So we're going to begin the fourth lecture by looking at the phenomena of paramagnetism, specifically about insulators and about looking at isolated atoms. Okay, so by isolated atom, I mean one in which the magnetic moment on one site doesn't interfere with the magnetic moment on another site. We'll call this this be known as Curie paramagnetism. And then the second part of the lecture will bring in the interactions between atoms, and we'll look at how that gives rise to a modified paramagnetic behavior, the so-called Curie-Weiss law, and how at low temperatures that leads to a magnetic ordering, which is what we might know as ferromagnetism, okay, permanent magnetic materials. So in one sense, a paramagnetic material is something the opposite of a diamagnet. So when we place paramagnetic material in an external magnetic field, its energy decreases. So paramagnetic materials want to move to regions of higher magnetic field. Okay. So we imagine our paramagnetic material as being comprised of some sort of magnetic dipoles, and these will align with the applied field. So what that means is the local field will be greater than the applied field because all of those magnetic dipoles enhance the field inside the material. That leads to a positive susceptibility. Okay, so chi is a positive number. But paramagnetism is generally very weak, so the induced field is very much smaller than the applied field. So the susceptibility chi is typically the order of 10 to the minus 5. So that's a little bit, maybe it's an order of magnitude or two bigger than diamagnetism, the opposite sign, of course, but it's still a very weak effect. Okay. Now, we'll look at the paramagnetism of metals in later lectures, but at least for insulators, where we can think of the atoms, the electrons in the atoms being localized, we find that the susceptibility is strongly temperature dependent. Okay, and we can sort of understand this in a sort of classical model at the moment. Okay, so this is where in a classical model of magnetic moments, the magnetic moment can point in any direction. Okay. So we're going to assume that these magnetic moments are only very weakly coupled to each other. What systems does that apply to? Well, if the system is a gas, that certainly applies. So for example, oxygen, O2, is paramagnetic in its ground state. And so a gas of oxygen behaves very much like is a paramagnet to a very good approximation. What about a solid? Well, typically transition metal compounds, very often the transition metals, as we saw in an earlier lecture, the transition metals can themselves have a magnetic moment. Okay, and in something like copper is a classic example. So if you take copper in copper sulfate, that's quite a good paramagnet and quite a good model for an isolated atom paramagnet, because the copper atom, which has the magnetic moment, is surrounded by the sulfate group. There's probably also some water in there as well. All of those ions are not they don't have a magnetic moment. So that means that the copper atoms are quite separated in space, and so the magnetic moment at one doesn't really interfere with the magnetic moment of another copper. So to a very good approximation, we can treat those transition metal compounds as isolated atoms. Okay. So if we think of the situation in which we've got no field, then in this classical picture, the magnetic moments can point in any particular direction they feel like. Okay, there's no interaction between them, so there's no correlation. So on average, there is no net magnetic moments. If I sum all the individual magnetic moments up, I get 0. And when I apply the field, we start to get an alignment. Okay, so there's an energy preference for them to align with the field. So if I look at this situation here, you can see there is a net magnetic moment pointing upwards. Okay. What happens as I increase the temperature? Well, you might imagine at very low temperature, there's a very strong energetic preference for these spins to align with the field. But as we increase the temperature, an individual spin can have enough thermal energy that it could decide to point against the field. Okay. So the magnetism will decrease as we increase the temperature. Okay. So we're going to expect a behavior of the susceptibility. We would expect that, if I was to plot chi versus the temperature, we'd expect some sort of behavior like this, where the susceptibility decreases like this. And so we'll find later on that we would expect that chi is actually proportional to 1 over the temperature. Okay. So let's now move and think about the quantum picture. Okay, because if we're thinking about paramagnetism coming from magnetic moments of atoms, that's always going to be the quantum picture. Okay, and so we'll consider perhaps the simplest case. So that's a site with spin a half. Okay, and that could just be an isolated electron, or it could be an atom whose net spin, where we have J equals a half. Okay, so we've added up all the orbital and the spin angular momentum, and the net angular momentum for the atom is J equals a half. Okay, and we'll see that. So in that case, we know that the G factor is equal to 2, and so I'm going to have my two energy levels. Okay. The magnetic moment so these are the magnetic moments. Okay, so the magnetic moment, and I should say that the external field, pop that on there. So this is my external field, is this way. So the low energy state is the one where the magnetic moment aligns with the field, and the higher energy state is the one where it anti-aligns. Now, if we remember that this is actually spin down, and this is spin up, because the direction of the spin and the direction of the magnetic moment are in opposite sense. Okay, so the equation that we would have for the energy of these levels, if we looked back, was the energy was equal to minus G, the magnetic quantum number, Mj. Let's see, what else do I need in there? I would need a mu b and an external field. Okay, so that's the energy of each of these levels, and so that's telling me that for the lower level, so we know that Mj is equal to plus or minus a half. That's the magnetic quantum number. So that is going to cancel out with the G. So my energies will be equal to plus or minus mu b times b. What did I call that? B naught for the external field. So this energy here will be equal to minus mu b naught, and this energy is plus mu b naught. And you will have done a very similar derivation to the one that we've done now with Jason when you did in the Michaelmas term, when you did statistical mechanics. But I'd like to just go through this one, thinking specifically about the magnetic case. Okay, that's set up some of the problem. I'll now switch to my whiteboard and go through this in a bit more detail. Okay, so we've got our two-level system. Let me just draw a little sketch of that in here. Here's my two levels. Remember, we draw on the direction of the magnetic moment, up and down there, and as a reminder, the external field B0 is pointing this way. Okay, and so the energy of these two levels, as we discussed on the previous slide, the upper level is plus mu b naught, and the lower level is minus mu b B naught. Okay. Now, this is in thermal equilibrium at a specified temperature, so I can use the Boltzmann distribution to find the probability of a state being either up or down. Okay, so we'll use the Boltzmann distribution. Now that tells me that the probability, Pi, is equal to e to the minus the energy of the ith level over kT, all divided by z, okay, where z is the partition function. And if you remember that z is the sum of all these Boltzmann weights, okay. So if I wanted the probability of being in the lower level, that's going to be e to the, now the energy is minus mu b b naught, so I have a positive on the top, so that's going to be mu b b naught over kt. And the partition function is the sum of all the exponential factors, so that's e to the mu b b naught over kt plus e to the mu b b naught over kt. Sorry, that's the minus, obviously. Okay. And the similar formula is going to apply for the one in the probability of being in the upper level. It'll be exactly the same, except now the energy is plus mu b b naught, so the minus sign appears in the top. And it's the same as the partition function on the bottom, so that doesn't change. Okay. Now, let's imagine that I have a number of these atoms prepared in an identical way, all at the same temperature. Okay, so let's imagine I've got n of those per unit volume. What is the net magnetism? Well, it must be equal to n times the magnetic moment of one of these. Okay, that's mu b, and it will be the difference between how many are up and how many, the probability of being up and how many are down. Okay, so this is p up minus p down. So remember that n here is the number of atoms per unit volume. Okay. So really what we've got is, if you like, we've got n times p up. That would be the number of atoms whose magnetic moment is pointing with the field. And we have n times p down. That would be the number of atoms whose magnetic moment is pointing against the field. So the total number, the sort of net effect, the number of atoms that point in the direction of the field is equal to the difference of those two things. And then if I multiply by mu b, that's the magnetic moment from one atom. So that would then give me the total number of magnetic moments per unit volume, okay, in the direction of the external field. And that's what our definition of M is if we go back to the first lecture. Okay, right, on with the math. So let's plug these things together. What are we going to get? N mu b. Now, obviously writing these little exponentials is getting a little bit tricky, so what we will do is we'll just define alpha. So this is e to the alpha minus e to the minus alpha over e to the alpha plus e to the minus alpha, and alpha is just mu naught b naught over k Boltzmann constant times temperature. Okay, so this we recognize as hyperbolic tan. So the final answer is n mu b hyperbolic tan of alpha, or if we like, n mu b hyperbolic tan of mu naught b over kt. Okay. Now this is valid for all temperatures, but very often we're going to be in the low field limit. Okay, and what do I mean by that? So we are typically in the low field limit, and that means that the energy splitting mu b times the field is much less than kT. Okay, for the magnetic fields that we can typically apply, the order of a few Teslas, this is going to be true. And we also know that tan of something small, tan x, is approximately x. Okay, we can look up the Taylor-Maclaurin series for that. So what this means is that the for this one above, tan of alpha is approximately mu naught b over kt. So we can go back and we can say, aha, well, so in other words, m is approximately in this limit n mu b squared that should be a b. I'm not sure why mu naught came in there. This is mu b. Here we go, over kt. Now, remember in the definition of susceptibility, so as mu naught times m equals chi b. Okay, so that defines the relation. This defines what chi is, the relationship between m and b. Here we've got a relationship between m and b. So chi in the low field limit is just n mu b squared mu naught over kt, which is a form of Curie's law because this is equal to c over t. So that was the same relation that we showed earlier on. Okay, that we expect the susceptibility to decrease as 1 over the temperature. Okay. We can see from the kind of quantum position, if we're at low temperature, everything wants to align with the field, and as I go to higher and higher temperatures, more and more of the atoms will have their magnetic moment aligned against the field. In fact, in the high temperature limit, we'd have as many pointing with the field as against the field, so the magnetism at that point would go away, and hence, the susceptibility goes to 0 as t goes to infinity. Okay, but very often we're in the we're typically in the low field limit. Okay, and here's that derivation written out somewhat more neatly. Okay, so just a reminder that in general, the magnetization in this material is given by by this expression here at the top in terms of the hyperbolic tan. But we're very often in the low field limit, okay, down here, in which case the magnetization follows this more simple relationship, and we see that as a various form of Curie's law, in the sense that the susceptibility is proportional to 1 over the temperature, and we often define C, the Curie constant. Okay, so that's the derivation for the spin half case. What happens for a general atom? Okay, we've looked at the transition metal and rare earth metal ions. We've discovered that they've got angular momentum J, and J doesn't have to be a half. It can be 2, 4, 5 over 2. Okay, a whole variety of different things. What do we do then? And unsurprisingly, the math is a little bit more involved. And to give you the headline result, what we have is the magnetization now is given by, again, n is the number of atoms per unit volume, g is the Landé G factor. We know what mu b is, it's the Bohr magneton, j was our angular momentum quantum number, and we introduced something called the Brouwan function. Okay, same Leon Brouwan, who developed Brouwan zones. And this Brouwan function looks like this. Again, unsurprisingly, it's a little bit more mathematically involved. It involves coth, which is the inverse of hyperbolic tan. Here it is there, and x is given here. Okay. Now, in order to derive this, if we wanted to do that, we can actually follow the same route as spin a half. Okay, we've got more levels to sum over, but we can define a partition function by just summing over our levels. We can then look at the magnetization that each of those different levels gives to us and work out what the net magnetization is. Okay, and it gets a little bit mathematically involved, although there's absolutely nothing that's beyond prelim math in there. Now, this I've set as one of the lecture questions that you can do in your tutorial. Okay, and I would say that there's a couple of parts of that which I've noted on the question, which are quite mathematically involved. And if you'd like a math challenge, by all means, go and do them. If you prefer not to, that's absolutely fine. I'm not going to ask you to derive this equation in an exam. I'm not going to ask you to memorize this in an exam. If you need to use this in an exam, you'll be given it. There's no point memorizing a complex formula like the Bro-1 function. Okay. So if you're interested, by all means, go ahead and do that question and see how the derivation works. I think it is quite instructive. But if you're just content to use this formula and see how it works, that again is absolutely fine. So there's a couple of later parts of that question after you've derived it, which you can just assume this formula and look at some of the limits. Okay, it's nice to show that this reduces to the formula that we've got when j is a half. It does. We could also see what happens as j goes to a very large number. Okay. But the limit that's potentially interesting is, again, that low field limit. Okay, so let's just have a play with that and see, does the general case follow Curie's law? Under these things. Okay, so we've got that m is equal to n lambda g factor mu b j and the Bro-1 function. Okay, and the Bro-1 function here is 2j plus 1 over 2j coth. I'm going to struggle to write this all in the space, I think. 2 plus 1 over 2j times x minus 1 over 2j coth x over 2j. Oops, just about fit that in. Okay. Right, so we're interested in the low field limit. And that means that x here is much, much less than 1. Okay. So what that means is I can use an expansion of coth. And if we look up the Maclaurin expansion for, say, coth y, that will be approximately equal to 1 over y plus y over 3. Okay. So what does the Bro-1 function become? It will be 2j plus 1 over 2j times, okay, 1 over the coefficient of coth, okay, 1 over y, so that's 2j over 2j plus 1, 1 over x. Okay, I'll do the next, the 1 over 2j term next. So that is minus 1 over 2j, and then the 1 over y gives me 2j over x. Okay, and happily you can see that these two terms cancel. Okay, so we don't need the first term in the expansion. What we do need is the second term in the expansion. Okay, and that is going to be 2j plus 1 over 2j times the coefficient with the 3 on the bottom. So this is 2j plus 1 over 2j x over 3. Okay, and minus 1 over 2j x over 3 2j. Okay. So if we now take these two terms, that's going to give me 2j plus 1 all squared minus 1 times x, and on the bottom I've got 4j squared, and I've also got a 3. So this is equal to 4j squared, expanding the bracket, plus 4j. The last term of the bracket will cancel with the minus 1, okay, which is going to be divided by 4j squared and a 3. Okay, I'm going to run out of space, but we'll see how we go. Okay, this is equal to the 4's cancel, the j's cancel, so I've got j plus 1. Oops, I missed the x out. X needs to go in there, doesn't it? Okay, 2j plus 1. So as the 4 cancel, I've got a j on the bottom, and I've got a 3 on the bottom, and I've got an x up the top. Okay, right. So now I can substitute in my value of x, and I can also substitute in my m, because I need m being equal to ng mu b j and the Brillouin function. Okay, and if we do that, the result is on the next page. Okay, so we're nearly there with our derivation. Let's just complete things. So what we found is that the Brillouin function in that low field limit is equal to j plus 1 x over 3j. Now remember that x is equal to j g factor mu b b over kt. Okay, and that the magnetization, which is what we're really after here, was n g mu b j times the Brillouin function. Okay, so we're nearly there. Let's substitute all that in. N g mu b j, Brillouin function, j plus 1 over 3j, and then we need the x. Okay, x was j g mu b external field over kt. Right, so grouping everything together, n, I'm going to have a g squared, I'm going to have a mu b squared, the j's, I'm going to get one j left on the top, and a j plus 1, and then on the bottom I've got 3 left over and a kt. So you see that this is a form of Curie's law, okay, whereby if I take what I might call mu effective, and that's equal to g mu b square root of j plus 1. Remember, that's the total magnetic moment that we defined earlier on. Okay, this is saying that the magnetization in the material is n times mu effective squared over 3 kt. Okay, so it's a very similar result to what we found in the spin half case. Right. So if we do the same trick there and convert this into, use the definition of the susceptibility, we obtain Curie's law again. Okay, so here I've got the susceptibility being related to 1 over the temperature, where there's an effective magnetic moment here. And so what we would do experimentally, if we wanted to work out what the magnetic moment of, say, paramagnetic copper sulfate would be, is you'd take a series of measurements. Okay, you'd plot 1 over chi versus t, and what you would find is these would lie on a some sort of straight line. Okay, it'd be a series of points that you might sort of measure. There'll be a little bit of scatter perhaps, but we'll look something like this, and the intercept will be very, very close to 0 here, and then by looking at the gradient, okay, the gradient is related to the effective magnetic moment. So that's how we could work out, if you remember the table we had in the earlier lecture when we looked at the total magnetic moment of atoms and ions. That would be how that's how those experimental numbers were obtained in order to compare to our Hund's rule model.